Today we are walking through the paper titled Latent Reasoning with Normalizing Flows.
What is the main question this paper is trying to answer?
The paper asks whether a language model can reason in compact continuous states instead of writing every intermediate step as text, while still keeping the useful parts of chain of thought decoding.
Why is ordinary text chain of thought costly here?
Text chain of thought makes the model verbalize each reasoning step as discrete tokens. That is convenient for sampling and scoring, but it can spend many tokens on thoughts that are semantic, uncertain, or not ready to be written in natural language.
Did earlier latent reasoning methods solve that trade-off?
Not completely. Coconut uses hidden states as thoughts, but those thoughts are deterministic, so there is no explicit distribution over possible reasoning paths. LaDR uses diffusion over latent tests, which is expressive. This comparison diagram shows the design space. Explicit Code moves through text tokens. Coconut recycles hidden states. LaDR denoises latent tests over several steps. And NF Code samples continuous thought tokens from left to right before producing the answer.
So the new part is not just using continuous states, but sampling them like a sequence?
Exactly. NF Code creates an LLM facing continuous thought space. A normalizing flow maps encoder-derived thought targets into that space, and the model assigns a tractable probability to each continuous thought token in causal order. The training pipeline makes that concrete. During training, a VAE encoder turns an explicit rationale into continuous targets. Shallow flow blocks map those targets into NF Code's thought space, and the same LLM backbone learns both the flow likelihood for thoughts and the cross-entropy loss for answer tokens.
What changes at inference time compared with training?
At inference, the VAE branch and shallow training blocks are skipped. The LLM samples predicted continuous thoughts directly in the NF Code space, keeps the original KV test, and then continues decoding text answers in the same causal stream. The explicit chain of thought baseline can be written as a sum over possible text rationales. The answer probability depends on first generating a rationale, then generating an answer conditioned on that rationale.
What does that equation say in plain language?
It says the rationale is an intermediate variable. TextCode makes that intermediate variable easy to handle, because it is just more language model tokens. But the price is that reasoning has to pass through a long written channel. NF Code then defines a left-to-right Gaussian probability model over continuous thought tokens. Each thought token is predicted from the prompt in the earlier continuous thoughts.
Why is the Gaussian form useful rather than just a detail?
It gives the model both sampling and exact likelihood for continuous thoughts. That is what lets the authors train the latent path with likelihood objectives, and later apply policy gradient reinforcement learning directly to the continuous reasoning trajectory.
What experiments did they use to check whether this helps?
The main evaluation is code generation, using MBPP, Human Evil, and Lev Code Bench v6. The comparisons include explicit code T, diffusion-based latent reasoning, and other continuous reasoning baselines, using pass 1 on pass K. This result plot asks what happens when the model gets more samples, on both MBPP and Human Evil. NF Code stays above the base model and LaDR across the range of K, and the gap remains visible even at large K.
The blue NF Code line keeps rising.
It shows that the latent reasoning distribution still has useful diversity. Sampling more candidate latent thoughts leads to better pass K, instead of collapsing into many near-identical attempts. The reinforcement learning plot separates token space GA RPO from latent space refinement. Token space GA RPO improves the low sample region but flattens at larger K, while NF Code with latent space ARL improves pass 1 and keeps the upward pass gate rend.
Why does preserving the large gate rend matter?
Because pass gate depends on variety as well as quality. If reinforcement learning only makes the first answer stronger but narrows the distribution too much, extra samples stop helping. NF Code's latent space update is meant to improve quality while keeping multiple useful reasoning paths available. The perturbation study checks whether the latent space is smooth. As noise increases, decoded surface text changes faster than functional agreement, which means different text can still lead to programs that pass the same tests.
So the latent space is not just memorizing one exact written rationale?
Right. The evidence suggests the space contains neighborhoods of related reasoning trajectories. Small perturbations can change the wording of decoded thoughts, but the resulting code often remains functionally consistent.
What is the strongest takeaway from all of this?
The paper's central claim is that latent reasoning does not have to give up the language model's native decoding interface. By using normalizing flows, NF Code gives continuous thoughts a probability model, keeps left-to-right generation, and supports both likelihood training and reinforcement learning.
So the win is both computational and modeling related?
Yes. The computational side is fewer intermediate reasoning tokens. The modeling side is that the continuous reasoning path remains probabilistic, scoreable, and trainable in the same causal stream as the final answer. Before we wrap up, there are two more implementation details that make the claim stronger: how the model is trained from text rationales, and how reinforcement learning can act on continuous thoughts.
How does the model learn continuous thoughts if the training data starts with written rationales?
The paper first uses a frozen text VIE encoder to compress an explicit chain of thought trace into continuous targets. NFGOT then maps those targets into the LLM-facing thought sequence, so the model learns a latent reasoning path and the final answer in one supervised objective.
Why do they use a staged training curriculum instead of training everything at once?
The first stage freezes the LLM backbone and trains the shallow flow blocks plus continuous thought projection layers. That aligns the continuous target space with the frozen language model. The second stage unfreezes the full model, so the backbone flow head and answer head can adapt together.
And reinforcement learning can update the latent reasoning path itself?
Yes. After supervised training, the paper freezes the shallow flow blocks and optimizes the policy directly in the LLM-facing thought space. The likelihood contains both the Gaussian likelihood of the continuous thoughts and the token likelihood of the answer. These equations show the latent part of the policy ratio. The per token log probability changes are summed across the latent sequence, and then exponents are aided with clipping so the update does not become numerically extreme.
What does that mean for the result plots we saw earlier?
It explains why the ARL result is important. The paper is not only tuning the final answer tokens, it is also giving reward feedback to the continuous reasoning trajectory. And the plotted Pascal curves suggest that this can improve early samples without destroying large sample diversity.
What should users be careful not to overclaim?
The evidence is strongest for the code generation benchmark studied here. The paper shows that NFGOT can preserve sampling, scoring, and decoding advantages while improving pass rates and reducing intermediate reasoning cost. But the broader claim still depends on how well this latent space transfers to other reasoning tasks. That wraps up this paper walkthrough. The main idea is simple but powerful. Keep the benefits of chain of thought, move the intermediate work into a compact continuous space, and make that space easy for the language model to sample and optimize.